Hello and welcome. In this session, we'll derive equation for frequency and mode shapes for systems with distributed mass. Now let's consider a beam having uniform cross section subjected to a general loading which is varying with respect to space as well as time. So we are denoting variation with respect to space by variable x and variation of time by a variable small t. Now there are mainly four beam theories. So we have Euler-Bernoulli beam theory, we have Rayleigh beam theory, we have shear beam theory, and we have Timoshenko beam theory with certain underlying assumptions. So for the sake of simplicity, we will be considering Euler-Bernoulli beam theory, which ignores shear deformations and rotary inertia. So that simplifies our derivation to a great extent, and for all practical purposes this Euler-Bernoulli beam theory is valid. Now if I consider a beam having uniform cross section subjected to a general loading which is Px comma t, and having constant mass, constant modulus of elasticity, and constant moment of inertia as per the assumptions of Euler-Bernoulli theory, and consider a very small segment of this beam having distance dx, we can draw free body diagram for the same. Now before drawing a free body diagram, we need to understand that at the start of this segment and at the end of this segment, the bending moment and shear forces will have incremental increase. So if I draw the free body diagram for the small segment in a magnified manner, so we have a shear force at the start of the span dx, and the moment which is acting in the clockwise direction, which is denoted as m. So at the end of this very small segment, there will be incremental increase. Now we are using partial differentiation here because there is variation of moment as well as the shear force with respect to time also, but that we are not considering. In this case, we are considering variation of bending moment and the shear force with respect to space. So we have m as the acting bending moment in the clockwise direction at the start phase of this small segment. At the end phase, to establish equilibrium, this has to act in the opposite direction, that is counterclockwise, and there will be small incremental increase over the distance dx. So we have dou m by dou x into dx. Now similarly for the shear force, we have the initial shear force as well as this small incremental increase, which is dou v by dou x for the length dx. So the dx also comes into picture. Now if you see the coordinate system that we are following, we have upward displacement as y. Now if we take first derivative of y, the displacement, we get velocity. So dy by dt nothing but velocity, and the second differentiation of displacement y with respect to time. So these differentiation are not with respect to space, these differentiations are with respect to time. So d2y by dt square is nothing but the acceleration. Now this system is not in the state of dynamic equilibrium because there is a force missing, which is the inertia force. So if you are familiar with the D'Alembert's principle, it says there has to be an inertia force acting in the direction opposite to the motion. Now if you see, the loading is upward, so we can assume that the displacement will be in the upward direction or the motion will be in the upward direction. So the inertia force F of I needs to act in the downward direction. Now the inertia force, you all know, is mass times the acceleration. Now mass of this beam is m. Now we are considering the small segment, so this mass becomes m into dx. Okay, so this entire term is nothing but the mass, and we need to multiply this with the acceleration term, which is nothing but d2y by dt square. Now this inertia force has to act in the opposite direction of motion, so it has to act in the downward direction. Now this gives us the complete dynamic equilibrium and free body diagram of the forces. So before writing the vertical equilibrium, let's establish few relations which we already know. There is a relationship between the shear force and the bending moment. Now here everywhere we are using partial differentiation because we are considering variation with respect to the span, that is nothing but the space x, not with respect to time. That's why we are considering the partial differentiation. So we know the shear force is nothing but the first derivative of the moment. So v is equal to dou m by dou x, and from theory of pure bending or simple bending we also know m is equal to ei into d2y by dx square, but here we are using dou 2y upon dou x square because we are taking partial differentiation with respect to space, not time. Now these two relations are important because we will be using them to get our differential equation. Now first let's establish the equilibrium, vertical equilibrium. Now we have to assume a sign convention, so let's assume the upward forces to be positive and downward forces to be negative for the equilibrium sake. So we have 1, 2, 3 and fourth one, which is the external force. So these shear forces and the inner shear force is internal force. So inertia force is anyway fictitious force, but the shear forces are internal forces, and this P of x comma t is an external force. So if we establish the equilibrium, we have this shear force at the start of the segment acting upward, that is the only positive force. Rest two of them will be acting downward, so we'll have to treat them negative. So let's consider the vertical equilibrium. So V is the shear force at the start of the segment which is acting upward. This is the shear force at the end of the segment acting downward with this incremental increase over the span dx, and we have this px comma t for the span dx acting in the upward direction. That's why we'll treat this as positive. We also have a inertia force, so this is mass m into dx, and this is the acceleration dou 2y by dou t square. Again we are considering the partial differentiation because we are considering variation of displacement with respect to time only, not with respect to space. So this entire thing has to be equal to 0 because we are establishing vertical equilibrium. Now if we simplify this, we know this v and this v can get cancelled if we take this minus sign inside. So this plus v minus v gets cancelled, and this minus will be attached to this dou v by dou x into dx. So this is what we are left with after cancelling the v. So this is nothing but dou v by dou x into dx. Rest of the terms are the same, nothing changes. Now if you see, we'll send these two minus terms on the right hand side and keep force on one side. So we'll have force either on the left hand side or on the right hand side. For the time being, let's keep the force on the left hand side and send the negative terms on the right hand side so that they become positive. So we have px comma t dx equal to plus of dou v by dou x into dx, and then plus m into dx into dou 2y upon dou t square. This is nothing but mass into acceleration, and this is the incremental increase in the shear force. Now if we take dx common, which you can see here as well as here, and we have dx here also. So if we take dx common, so dx comes out of the bracket and this everything comes inside the bracket. We have dou v by dou x, that is the partial differentiation of shear force with respect to the space, and m into dou 2y upon dou t square, and dx, this dx and this dx gets cancelled. So we have external force px comma t and the incremental increase or whatever is the left in this bracket, so dou v by dou x plus m into dou 2y upon dou t square. Now let's rearrange this as we do in the single degree of freedom system. We keep all the forces on the left hand side, the reactive forces, and the external force on the right hand side. So we keep external force px comma t on the right hand side just to be consistent with what we are following in single degree of freedom system. Now in this equation, this v we can replace because we have relation between this v and the bending moment. So this equation is nothing but, or this relation is nothing but, shear force is equal to first derivative of moment with respect to space. So that is nothing but this v will be dou m by dou x. So we'll replace. Now once I replace, if you see, this dou by dou x comes out and we are replacing this v by dou m by dou x. So this dou by dou x comes out and we are replacing this v by dou m by dou x, and rest everything is the same, m into dou 2y by dou t square. Now and the right hand side has the external force px comma t. Now here if you see, this dou by dou x and this dou by dou x gets multiplied and it becomes dou square by dou x square m. Okay, so this is the product of this, and rest everything stays the same. Now again we have a relationship for this m. This m can also be replaced. So we have its relation with respect to displacement as ei into dou 2y upon dou x square is nothing but the bending moment. So this dou square upon dou x square stays the same, but this m will replace with ei into dou square y upon dou x square. Okay, so let's replace this. So this dou square dx square comes out, okay, and this m which was there in the equation gets replaced with ei into dou 2i upon dou x square. Rest everything stays the same. Now again, if you see this dou square upon dou x square into dou square upon dou x square, this gets multiplied and this will be the fourth order now. So dou raised to 4y upon dou x square. Now this ei is again there, so we'll write the constant. See, as we have assumed, ei is going to be a constant, so this ei comes out. Now we have dou raised to 4y upon dou x square plus this m is the mass, which is constant again. Now we have dou square y upon dou t square, which is as it is, and then we have the force, external force px comma t. Now if you observe very carefully, this ei and this m, which is the mass, don't confuse this with moment. Moment is denoted by capital M and mass is denoted by small m. So these three terms are constant, which we have assumed for Euler-Bernoulli's beam theory. Okay, now this is the fourth order partial differential equation, but this is an approximate equation because it has the underlying assumptions of Euler-Bernoulli beam theory. That is, it is not considering shear deformations and ignoring the rotary inertia, as well as it is not considering flexural effects due to axial forces. So these are the limitations of this equation A. But for the sake of practical purposes and to reduce the complexities, Euler-Bernoulli theory is quite acceptable. Okay, so now let's consider the free vibration of this. So we'll have to ignore the external force. So the free vibration, as you have studied in a single degree of freedom system, you must be already familiar that the external force is not present during the vibration. So there is certain initial condition imparted and the system vibrates on its own. That means the right hand side of the equation, which is the external force, we'll treat it as 0 for the sake of free vibration analysis. Okay, so we have the same equation but rewritten with right hand side to be 0. ei into dou 4y upon dou x square plus m dou 2y upon dou t square. Now here we have two different variables. One is space variable x and the other one is time variable, which is t. But the right hand side now has become 0. That means this is fourth order homogeneous differential equation. Okay, now to solve this we have to use a technique called as variable separation. So we'll have to separate x and t and assume the solution as the function of these two. Okay, so let's assume the solution y x comma t be phi of x and f of t. So the product of these two is nothing but the solution of the equation which we have here, the differential equation of fourth order. Now as per the assumed solution, we'll replace wherever we see y, we'll replace this with this phi of x and f of t. Okay, instead of y, we'll just put phi of x and f of t, the product of these two things. ei into dou raised to 4 upon dou x raised to 4 remains as it is, and we'll replace this y with phi of x and f of t. So here what is written is exactly the same, replacing y with phi of x and f of t. Here also we have y, so again we'll replace that y with phi of x and f of t. So m into dou 2 upon dou t square phi of x into f of t, this is equal to 0. Now here we have, when we take differentiation with respect to x, the time term is treated as constant. See, this is a partial differentiation, so whenever I am differentiating with respect to x, the t term will be treated as constant. Whenever I am differentiating with respect to time, the x term will be treated as constant. Okay, so we'll rearrange this equation, and now ei is a constant. For the differentiation with respect to x, t can also be treated as a constant. So this ei and this f of t is treated as a constant. So ei into f of t. Now this dou raised to 4 upon dou x raised to 4 now need not to be a partial differentiation because we are differentiating x with respect to x. So we'll consider the full differentiation. So this becomes d raised to 4 phi of x upon dx raised to 4 plus this mass is there. Now phi of x will come out because this differentiation is with respect to time, so only differentiation possible is of f of t. And now again we need not to consider the partial differentiation because we are differentiating function of t with respect to t. So this becomes d2 f of t upon dt square equal to 0. Now this expression can further be rearranged. So if you see, I can shift this time terms on one side and x terms on the other side. So we will make sure that we separate out the terms and bring them on one side. So f of t will send on the right hand side and phi of x will bring on the left hand side. So if you see, ei is there, then d raised to 4 upon dx raised to 4, phi of x is as it is. Now we are bringing this m and phi of x on the left hand side. So this m comes here, okay, so this m from here comes here, okay, so this is the m that we have, and then we have phi of x coming to the left hand side, so again it will go in the denominator, so it becomes 1 upon phi of x, and this f of t we are sending on the right hand side, and this term as it is, d2 f of t upon dt square, and this f of t goes in the denominator again. This minus stays as it is, so this becomes 1 upon f of t into d2 f of t upon dt square. Okay, now we'll replace this fourth differentiation for x as a Roman letter and this second differentiation with respect to time with 2 over dots. This term becomes fourth differentiation of phi of x, so phi raised to 4 of x, this phi of x comes in the denominator, so this phi raised to 4 upon phi of x, right, is equal to, now this f of t, now this minus is as it is, if you can observe, this minus stays here. Now this is the second differentiation of f of t with respect to time, so we are denoting that with 2 over dots like mu double dot or whatever you have followed in the single degree of freedom system. The same approach we are following, and f of t which is remaining in the denominator, it is as it is. So this is a very important expression that we need to consider. Now if you observe, this equation p has two different differentiations. One is with respect to x and the other is with respect to time. For the equation p to be true, they must be equal to a constant. Okay, so the LHS and RHS independently should be equal to a constant. Okay, so let's assume that the constant to be omega square. Now why we can assume any constant, but we know we denote frequency by omega. So we will be considering this to be omega square. It can be any constant, but for the sake of derivation we are considering that constant to be omega square. Now the left hand side and the right hand side can be equated to omega square independently, and we are more interested in the frequency and the mode shapes, so we are more concerned with the left hand side portion of this expression than the right hand side of this expression, which we'll subsequently see in the next part of the derivation. Stay tuned.